I introduce myself. I'm Edoardo Provenzi, and on the behalf of Michel Berthier, I will present this paper called Hans colorimetric effect from a quantum measurement viewpoint. Okay, can I start? Mm-hmm. Okay, so, okay. 2 years ago in Toulouse, we introduced this idea that color perception can be studied through a quantum-like framework. And we got some advances in these 2 years. And in the first part of the talk, I will present, we introduce some results that we obtained, which, by the way, are fundamental in order to understand how to interpret and study the Hans colorimetric effect inside our model. Okay, first of all, we would like to start by quoting this beautiful picture. That is the first geometrization of color that was proposed by Newton himself in 1704. And Newton, starting from his very famous experiment in which he showed the existence of pure lights, monochromatic components of light by the prism, he decided to put these monochromatic lights at the perimeter of a disk to set a chromatic light, daylight, in the center of this disk, and to measure the pureness, what nowadays we call the saturation of color, as the distance between the center and the perimeter. We will see that thanks to our model, we can give a formalization of Newton's idea. Okay, before starting, we would like to stress that what we study is a very simple configuration, that is this one on the left, which is a simple color stimulus embedded in a uniform background, nothing more, nothing less. There are at least two different frameworks in which we can study this situation. This framework here is the framework that have been studied by the CIE. CIE is the acronym of Commission Internationale de l'Éclairage, International Commission of Illuminant, and they decided to study color perception through what is called a metameric reduction of the infinite dimensional space of visible lights to a three-dimensional space. For example, you can imagine the RGB space. Instead, other researchers, for example, Oswald, Devalois, us, but other people, decide to put themselves here. So to study not the interaction between physical lights and the retina, but to study the properties, the intrinsic properties of perceived colors. We will see that these properties are nice and numerous enough in order to study the space of perceived colors without resorting to the incident light. Let's see how to do it. The first hint is the fact that thanks to the experiment of Newton, Maxwell, Young, von Helmholtz, and Grassmann, Schrödinger in 1920 came out with a set of axioms to describe the properties of color perception. And these axioms can be resumed by saying that the space of perceived colors is a regular convex cone of dimension 3. We have to wait until 1974 to find another property that was pointed out by Resnikov in a beautiful paper of 1974 called Differential Geometry and Color Perception, in which he exhibited a transitive group action on the space of perceptual colors, making it a homogeneous space. That was a brilliant idea because thanks to the classification of a homogeneous space and also with these properties of a regular convex cone, there are only two possible geometrical structures for the space of perceptual colors. The first one is the one that is considered by the CIE. That is 3 copies of positive real numbers. It is, of course, a flat colorimetric space, and all the RGB-like colorimetric spaces are like this. Instead, there is another possibility that was absolutely, let's say, not taken into account until today, and it is a curved space with a negative curvature -1, so a hyperbolic space, and it is the Cartesian product of positive real numbers with a hyperbolic model. And in Resnikov's paper was SL2R quotient SO2, but we can also give alternative representations, for example, 2 by 2 positive defined real matrices or the future light cone in the three-dimensional Minkowski space. And in the final part of Resnikov's paper, he used Jordan algebras as a framework to unify the two models. Let's see how. It turns out that C1 and C2 are the only positive cones, that means the interior of the set of squares of these algebras, that are non-isomorphic and correspond to three-dimensional formally real Jordan algebras. And the first one in particular, C1, corresponds to the positive cone of this Jordan algebra here with this Jordan product. And the second cone corresponds to this Jordan algebra here, that is the Jordan algebra of symmetric 2x2 real matrices, parameterized like this, and with this Jordan product that is called matrix Jordan product, that is isomorphic as a formally real Jordan algebra with this other one that is called a spin factor. And the spin factor has this Jordan product here that you can see. I don't think that you can see, but now you can see, I hope. Okay, here. So Schrödinger and Resnikov axioms can be resumed just by what we call a trichromacy axiom. That is, C is the positive cone of a three-dimensional formally real Jordan algebra. And in spite of the fact that this axiom is very abstract, it has the advantage that we don't have to specify a group action, because it is a controversial issue in Resnikov theory, and it is automatically valid if we assume this axiom. And more importantly, Jordan algebras provide a tool to build a coherent quantum-like theory of color perception. And since we want to be very precise and motivate why we want to study color perception through a quantum theory, before starting with technical details, we want to give a mathematical motivation and a perceptual motivation. So the mathematical motivation is that on one side, as you have seen before, Jordan algebras appear naturally when we study color perception properties. And on the other side, it is well known that non-associative Jordan algebras also appear in the formalism of quantum mechanics. And on the perceptual side, of course, the visual chain starts with the capture of a photon, so a quantum relativistic particle, by the retinal photoreceptors. And the correct interpretation of a perceptual color is an observable interacting with the visual scene that represents the state, and the human visual system that is the measurement instrument. Of course, it's not an electronic instrument, but it is a psychological and biological measurement instrument. And moreover, finally, repeated and identically prepared color matching experiments in order to measure color do not give a sharp result, but a distribution of color selection from a palette of colors. And so this is an intrinsic color feature that is very much like the probabilistic interpretation of quantum mechanics. So you can see that there are many motivations to study a possible quantum-like theory of color perception. And of course, we have to build the vocabulary of our theory, and this is it. First of all, we call a visual perceptual system V a visual scene where we can perform psychovisual measurements in isolated condition. Perceptual color state is a preparation of V for color measurements, exactly as we say in quantum mechanics. The objects of measurement are the observable of V, and they belong to a non-associative three-dimensional formally real Jordan algebra A. Perceptual colors are identified with unsharp observables using the language of quantum mechanics, and the measurement of a perceptual color on a state is registered as a perceived color. So please notice the difference between perceptual colors, which are unsharp observables, and perceived colors, which we identify with effects, quantum effects. And this is a radical change of paradigm with respect to the classical colorimetric theories, because in general, we specify colors through three coordinates, RGB. And instead here we have a theory of states in duality with observables and effects. So since I don't know if I will keep the time, this is a list of results that we have obtained, then we will see how much of these results I can discuss. So the first result is that we gave a mathematically rigorous definition of chromatic attributes as hue, saturation, and lightness. Herring chromatic opponency is exhibited in a natural and intrinsic way within our framework. We have proven theoretically the existence of uncertainty Heisenberg-like relations for chromatic opposition. We have proven that the Hilbert-Klein hyperbolic metric is a suitable candidate to measure perceptual color distance. And we also showed the relativistic nature of color perception because state changes after color measurements can be represented by Lorentz boosts. And we also applied this to white balance. And finally, we proved that we can obtain a finite volume in the infinite cone of perceptual colors by considering quantum effects and also explain Hans effects. That is the final part of this talk. So now let me introduce the technical details. First of all, of course, we have to define states of our theory, and the states are described by density matrices, which are, of course, positive semi-defined matrices with trace 1. And the space of all state is parameterized like this. And V1 and V2 are the components of a vector which belongs to the unit disk in R2. And this suggests a polar parametrization. And when we use the polar parametrization, we obtain this representation here of a density matrix. And when R is equal to 1, we obtain pure states. And when R is between 0 included, 1 excluded, we have mixed state. And of course, as you know, a finer description of state purity is given by the von Neumann entropy. In our case, the von Neumann entropy can be written like this. It is a radial concave function that has this expression, and it can be prolonged by continuity to R equal 1 by setting the von Neumann entropy to 0. Since the von Neumann entropy is the expectation on information gain after our measurement, von Neumann entropy equal to 0, it means that we have a maximal information when we are considering pure colorimetric states. And instead, we can also compute the maximal von Neumann entropy that corresponds to the minimal amount of chromatic information, that is rho 0, and it's nothing but the half of the identity matrix. And the achromatic state, rho 0 can be written like this. So it's a convex combination of pure chromatic states appearing with identical probabilities. And since we don't have chromatic information, we call this state the achromatic state. Instead, when R is 1 and theta is free to run between 0 and 2 pi, we have pure hues, which formalize Newton's spectral colors. Finally, we have to, if we want to formalize a Newton color disk, we also have to formalize saturation. And we propose to use von Neumann entropy to formalize saturation, of course, through this formula here, that allows us to have 0 saturation in the center of the disk and 1 on the border. And we just discovered that this also agrees perfectly with the concept of relative entropy between the state and the achromatic state. So, as you can see, Newton's idea can be formalized precisely through this quantum-like framework. Then there is also a very, very important thing, that is we can reparameterize density matrices written in polar form through this formula here, which is extremely important because, as I said before, this is considered as the achromatic state. These are two opponent states because they lie on antipodal points of Newton's disk, and this one too, and they are orthogonal to each other. They belong to orthogonal axes. And in fact, they can be interpreted as chromatic opponencies. So there is a balance between achromatic state and opponencies, chromatic opponencies. This is exactly what Herring theory predicted, and it has a biological counterpart in the action of ganglion cells that is represented here. The role of real Pauli matrices. Our theory is a real quantum-like theory. So we don't have the third complex with complex entries Pauli matrix. We just have two real Pauli matrices. And when we compute the expectation value of Pauli matrices on a given state, we obtain these two values here, which are nothing but 2 times the degree of chromatic opposition. So Pauli matrices carry a very important information, that is, they measure chromatic opponency. Okay, we also discovered that there is the possibility to find uncertainty relations related to Pauli matrices, and these uncertainty relations are written like this. And as you can see, there is no uncertainty only in the center of the disk, a chromatic state, or when we are on the opponent axis. But for example, imagine that we are here. So just for the sake of an example, orange, it means that these uncertainty relations means that we cannot measure simultaneously the presence of red-green, the opposition red-green and yellow-blue with absolute precision. And actually, there is a way to test this prediction through a procedure that was popularized in the 50s by Urwich and Jameson that is called hue cancellations. And we want to set up an experiment with some colleagues in Norway in order to test these uncertainty relations. And finally, the role of effects. So effects in our framework are nothing but matrices that belong to this space that are positive semi-defined, and also the identity minus this kind of matrices is also positive semi-defined. A straightforward computation leads to computing the effect space in which there is this parameterization here with alpha belonging to 0, 1, and V1 and V2 satisfy this inequality. And if we develop the geometrical representation of this space, we find this double convex cone, which, as you can see, agrees perfectly with the so-called Ostwald color solid proposed on a purely intuitive basis in 1916. Okay, so the use of effects that we have proposed, in our opinion, satisfy an elegant solution to a long-lasting problem. That is the fact that if you consider the original infinite cone of Schrödinger and Resnikov, you are doing the modeling of so-called ideal observers that respond non-trivially to any color stimulus. Instead, real observers, us, are subjected to the so-called glare limit, which means that beyond a certain light level intensity, photoreceptors bleach and we lose our perception abilities. So we must have this double cone structure. And let me arrive to the final part of the talk that is related to the Hunt effect. And so if we identify a perceived color C with an effect, then we can measure, of course, a color through, on a state rho. And if we consider as a particular case rho equal to rho 0, that is the achromatic state, and we perform the computation, we obtain exactly alpha. So alpha, since we don't have any chromatic information in the achromatic state, we associate alpha with what we call magnitude. That is a neutral name to avoid using lightness or many other names that can be, or luminance, sorry, many other names that can be a little bit misleading. There are many possible names to call this this quantity here. We simply call magnitude. And instead, if we compute the expectation value of the effect on a general state, we obtain this expression. And this expression is particularly intriguing because, as you can see, it mixes magnitude, so luminance of the color, with R. And R, if you remember, is related with the concept of purity. So we call it purity degree. And so through this very simple formula, we can see that the magnitude, the intensity of a color and its purity are not separate colorimetric attributes, but they are fused together. And this allows us to study the Hunt effect. The Hunt effect, so Hunt is a colorimetric effect. So let's call it a Hunt phenomenon. It's not a quantum effect. So the Hunt phenomenon in general is represented like this in the literature. And it says that the colorfulness of a color increases with its magnitude, its intensity. And we defined precisely the intensity, the magnitude. We didn't define precisely in this talk, we are working on it, colorfulness, but for the sake of the interpretation of the Hunt effect, the only thing that we need is to consider colorfulness as a monotonically increasing function of the degree of purity R. And we can understand, as we will see in the next final slide, Hunt effect by considering the three portions of the double cone effect. Let's see how. So if we consider the bottom part of the cone that is parameterized by alpha between 0, we avoid the 0 because it's the absence of light. So between 0 excluded and 1/2 excluded, we have that the expectation value of C on rho is maximal and equal to 2 alpha, which is strictly inferior than 1 when R is equal to 1. So even for pure state, we cannot reach 1. Instead, when alpha is equal to 1/2, we have what a great colorimetrist whose name is de Valois called the adaptation state, which is the state in which the human visual system places itself naturally if light is not too bright or not too dim. And when we are in this condition, we have that the expectation value of C on rho is maximal and equal to 1 precisely when R is 1, so for pure state. So it's the best possible condition. Instead, if light is too bright, so we are in the upper part of the double cone, we have that if we do the computation, we obtain this relationship here. And we can see that the expectation value of C on rho is maximal and equal to 1 when R satisfies this equation. And for non-pure state, that is very important to underline. For example, if alpha is equal to 2/3, then the expectation value of C on rho is 1 for R equal to square root of 2 on 2, so roughly 0.7. This can be resumed by saying that when alpha increases, we reach faster the sensation of a maximally saturated color with respect to the purity degree R of the state rho R theta. So as you can see, the use of effects allows us to study not only the possibility to confine the infinite cone of perceptual color to the finite volume double cone of perceived color, but also to study the Hunt effect. And we are using effect also to study many other properties. But this will be for the next GSI. This is a biography of some papers that we wrote during these years. And of course, I thank you very much. And if you have any question, I'm here. Michel, can you hear me?
Can you activate your microphones?
Yeah, of course.
And the camera.
Okay.
Perhaps, yeah. Stop.
Can you see me?
Yeah.
Yeah.
Oh.
I want to apologize. It was not possible for me to be with you today. I'm sorry because of sanitary conditions. And is there any question for Edoardo Provenzi?
Yes.
Yeah, can you come forward soon and put out the mask to speak to the speaker? Yes.
I would say for Edoardo Provenzi and Michel Berthier.
Just here, you're in front of the camera. Yeah? And
okay, the complicated is asking.
No, it's because the camera is here. The camera is here, okay? So put out your mask and speak. Like that,
right.
Yeah?
Okay. So it seems that your theory describes one qubit, right?
Yeah, it's one rebit actually, because it's a real qubit, a rebit.
I see. So, so the first question I have is, can you make predictions using your theory that have not yet been described in the theory? Or is it purely sort of retrospective.
Mhm.
The second question is, can you also model things like interference? I think it's hard because you have one qubit, but is there maybe an extension of the theory with multiple qubits, and then you can do things like interference and Bell inequalities and these type of things, real quantum things?
Okay, so if Michel agrees with me, I will reply to the first part of the question, and Michel replies to the second part of the question. So we split half half. So the first part is that yes, for example, it is impossible to obtain uncertainty relations using the CIE colorimetric theory. So this is something that we predicted. We can also predict in this talk we have proposed a qualitative interpretation of Hunt effect, but in another paper that we sent to a review, we proposed sorry, I said qualitative, and now we propose a quantitative measurement of Hunt effect. And so these are already two things. Then, yes, we are also studying in this moment dichromatic vision. And we are making novel predictions about the vision of dichromatic people and anomalous trichromatic people. And Michel, did I forget something about new predictions of our theory?
I don't think. I don't think so.
And for the second part, I think that Michel wants to say something. So,
yes.
Okay.
Yes, I think that we are going to work on chromatic induction. And it seems that it is very closely related to quantum channel, and in fact to measuring open quantum systems using quantum channel and Stein-Spring theorems. I don't think if I answer your question.
Well, I just wonder, is there like things like entanglement?
Yes.
And like even,
yeah.
So then the question becomes, do you get true Bell inequalities? That means that it's absolutely, then it's really quantum, right? If there's a Bell inequality, there's never going to be any local, let's say, classical theory that can ever predict that. Would you have things like that in your theory?
We don't have some kind of Bell inequalities for the moment, but we think that, as I said, Edoardo, at the beginning of his talk, this work that has been presented is in the very special case that we have only one color to measure and it doesn't interact with other colors. So when we want to study chromatic induction, for example, we have to place a color in the background and move the color of the background, and then we can expect that we can have some quantum channel effects, and maybe if we add more and more colors, something that is related to Bell inequalities.
Thank you very much.
Let me also underline one thing. We believe that also uncertainty relations are enough to say that it is a real quantum-like theory, because you cannot have uncertainty relations in a classical theory.
But you can, right? If you do a Fourier analysis, if you describe your theory with a field, even optical, theory is completely classical, but you have uncertainty relations between momenta and position. That's pretty classical. I don't think that's very quantum.
No. I don't agree with you in the sense that the simultaneous measurement of for example, chromatic opponency. If you cannot have the simultaneous measurement of chromatic opponency, then this is not. You cannot represent this through a classical colorimetric theory.
Yeah.
Just one more question.
I just arrived, but do we have absolutely the same formalism in signal analysis? With Gabor analysis, you cannot at the same time measure a frequency and the time at which it's like in music.
Mm-hmm.
You have exactly the same type of example.
The uncertainty is the properties of the Fourier transform, and in quantum mechanics, it is because impulsion and position are adjunct variables that are exchanged with the Fourier transform. So this mechanism is general and is due to Fourier transform, but the main properties of quantum mechanics is that it is a non-commutative space. The variable do not commute, and in the Jordan algebra frameworks, this means that the Jordan algebra is not associative. Is not associative. It is commutative, but it is not associative, and this translates the usual non-commutativity of quantum mechanics.
Exactly, because the two Pauli matrices that we consider do not commute.